Grant, thank you everybody. I'm going to talk to you about a process that Mark Lippett announced earlier. It's our latest generation X-Core, which is completely RISC-V compatible. And I'm going to particularly focus on our multi-threaded aspect and how we do the multi-threading. So just a bit of background. We are a fabless semiconductor. We've been making microcontrollers for the last 15 years. And their general purpose. So the same microprocessor goes into an audio board, sits in a little robot spider, controlling 26 different servos and doing the inverse kinematics. It's all about real-time stuff. So our latest generation, we're going to drop the strictly proprietary ISA that we have and replace it with a RISC-V ISA with a few extensions. So the reason we do multi-threading is because it exposes real-timeness in a software environment. So you can, from software, control very hard real-time tasks. And hard real-time here means sort of 2-3 nanosecond precision. That is the level of real-timeness that we're concerned about. And what it gives you is the ability to, in software, model all bits of hardware that you would need, provided the interfaces aren't stupidly fast. So up to about 500 megabits, up to latencies of about 10 nanoseconds we can deal with. But many interfaces like SPI, I2C, they're all much slower than that. I'll get in detail why it happens. The challenge is to make a large pool of threads very cheap, because then you can throw those threads away at tasks that need them, real-time tasks in our case, without being concerned that you've lost many thread contexts. So what we do is we have a single pipeline with a large number of register files, one per thread context. And the single pipeline executes those threads through it. So we completely expose the pipeline to the programmer. It actually isn't there. There's no forwarding or anything like that in there. And a thread can only be in the pipeline in one place. So once a thread has entered the pipeline, it can't re-enter it until it has completed, which means you need at least 5 threads to utilize the processor at 100%. So we got 8 RISC-V hearts inside each processing, and the 8 threads are time sliced over this pipeline on a per cycle basis. So every clock cycle, the next thread goes into the pipeline. We also have multicore, and multicore means that we have multiple blocks, each with 8 hearts in it. And the reason we do multi-core is because memory doesn't scale very well physically. There's just a limit to how much memory you can stick in a core before it bloats the core and it makes the core very slow. In our current process node, it's about half a megabyte we can stick in there. But people might want a megabyte or 2 megabytes, and we distribute it across multiple cores. Alternatively, we could have a system with caching, a cache architecture that would make the real-time aspect much more difficult to argument with. So we use distributed memory across multiple cores, and each core offers sort of a shared memory to the 8 thread contexts. So this is a picture of what it looks like. There's 8 hearts on the right core, 8 hearts on the left core. Each of the cores has a single execution unit that does floating point, integer, vector arithmetic, and they have a tightly coupled level 1 memory that they communicate with. And then there's a few other blobs on there. The most important one being the interface between the execution unit and the outside world, something that makes electrical levels visible to the execution unit and vice versa. It is a very small blob. It does a bit of serialization, deserialization, and that's it. It gives you the opportunity to double buffer I/O, so you can set some I/O going, do some compute, reconnect with I/O, and thereby executing protocols in hardware. So we have many cheap hardware threads, and you can think of them in analog to the idea of a sea of gates as a programmable blob. This is a bag of threads. You have a large number of threads, and you use them the way you would like to use them. Some people might use them all for DSP, other people might use them for I/O, other people might mix them up a bit. So you can use them for all those tasks, from control to DSP, to neural networks, to DMA engines. There is no DMA engine on our chip. If you like DMA, you use one of the threads, and it is the most programmable DMA engine you can think about. But it has a guaranteed time slice of memory, and because there's a guaranteed time slice of memory, you don't disturb any of the other threads whilst doing the DMA. Gather, scatter, it's all part of how you program that DMA unit. Right. So the bit that I would like to focus on is how we manage those threads in a RISC-V world. And the thread contexts are programmed individually. So they're MIMD processors in that sense. But you somehow need these threads to cooperate. And the mechanism we offer as a native mechanism for them to cooperate is a barrier mechanism. So a thread, the green one on the top right, is the parent thread. The parent thread can allocate a barrier and then use that barrier to attach a number of child threads and then iterate over this barrier many times for the child threads to make steps until they finally join. When the processor comes out of boot, there's just one thread running. Thread 0 is always running. Thread 0 is the thread that would normally boot itself from an external flash. And then after that, these threads live in a cooperative world. You don't need an OS, but you can run an OS on it if you want, something like FreeRTOS. Or otherwise, you can run things on the metal. So this model is very close to a fork-join processing model, right? Where you fork out, you process in whatever way you fancy, and you join up in the end. The nice thing is the way we've implemented it, these barriers are single cycle instructions. So if these parent and child threads are closely taking the same amount of time, you actually lose very little in terms of overhead. There's multiple barriers. So a child thread may decide to create fork and join parallelism inside its own world, if that's useful. So there's various ways in which this can be used. So let's take a look at what this looks like. On the left, we have the code that is executed by the master. The blue code is the code that's executed by the child thread, the children's. And then on the right is the same picture. So the first thing is for the parent to get a barrier. Then the parent gets all the all the children they need. I left out a code that sets up the children. You can set the program counter, you can set some of the register values. And after that, you synchronize. That starts all the threads. You execute any code you like, and you synchronize. And you do that as often as you need until at the end, you do a special instruction, which is a join instruction, and the join instruction will yield all the child threads and free them up, and you're finally done, and you can free the barrier. This mechanism allows you to dynamically allocate barriers, allocate child threads, and run them. You don't have to do it like this. We also offer the mechanism running threads asynchronously, but asynchronous threads will need a different mechanism to synchronize. Interestingly, on the synchronization, all the threads know, of course, that all the memory is now in a consistent state. So you can program these in any way you like and have knowledge where you are in the process, just standard programming techniques there. So, the question is, how do we manage those hearts? And there's two ways we can manage them. That bag of threads, we can either run it without an OS, and that is what we call on-the-metal approach, where all the operating system functionality is embedded in the processor. You use the barriers, the thread management from the processor. And the threads are explicitly allocated by the program, and that's the hearts are explicitly allocated. Now, when a software task is waiting, and a software task owns a thread, that heart will be taken out of the pipeline, and therefore eventually you will lose performance. The good news is the hearts will keep their state whilst they're not in the pipeline, so you can set up one of these threads on the metal to have the right state waiting, and on that state they will continue. Right? The bad news is, because it keeps the state in the register file, you can't use that thread context for another thread at this stage. So what you're trading in is the ability to respond quickly, and what you're losing is some of the cycles in your pipeline. This is why we have a pipeline that is 5 deep, and there's 8 threads, so you can soak up some of those cycles that go missing. On the other hand, you can use the operating system approach. And the OS approach means you deploy an OS, something like FreeRTOS, but it could be any OS that is small enough to sit in our memory. And it manages all hearts, one heart, however many hearts you would like to allocate to that operating system. And in the OS approach, when a software task is waiting for I/O, communication, whatever, the OS can reschedule another task in, and it will do that by saving and restoring the thread context in some piece of memory. So it makes better use of the hearts at the expense of not having as good a real-time property. Saving all the context will take a while, right? What we're talking about here is tens or hundreds of microseconds of time between context switches. So on the right is sort of soft real-time, on the left is hard real-time, and an application, such as the green blob in the middle, you can mix and match the two. You can say, I have 16 hearts, I'm going to allocate 3 of them to FreeRTOS, the other 13 I'm going to program on the metal. Those 13 are going to do some hard real-time tasks. The 3 on the right I'm going to use in FreeRTOS, and I'm going to do some user interface where 10 microseconds is here nor there. The interesting thing of the on-the-metal approach is it is a very power-efficient way to do things, because you're not saving and restoring state the whole time, right? You're literally just keeping the state in there and keeping it alive. So with the quick response time comes a highly efficient way of doing it. So the last bit I want to talk about is what else we had to do with RISC-V. We went from a bespoke instruction set to the RISC-V instruction set. And the biggest problem for us is, because we want to take all our customers with us on this journey, we need to find a way to achieve the same density that we had before and roughly the same execution speed as we had before. So to this end, we needed a compact instruction set, and there's the RISC-V C extension, but it didn't give us the execution speed we needed. So we had to take the decision to hijack the compact instruction set space and make our own version of that, which is an odd mixture, or in our view, a very nice mixture, of both compact encodings and dual issue encodings. So the C extension offers 48K of short encodings, because there's 2 bits at the end that can have 3 values times 16 kilobyte. We have a different user dead space where we have 32K short encodings, which are the instructions with a 0 at the end. They are the blue encodings. And we have 32K pairable instructions, we call them. And they are encoded in 32 bits, but have a hole of 15 bits, which fits a short instruction. And what it gives us is the ability to write code that uses the 32K short encodings, which gives us compact encodings for all the commonly used operations. And then it gives us the option to pair them with the green instructions, which gives us VLRW execution of 2 short instructions at a time. Now, 2 to the power 15 encodings isn't a lot, so we operate on a subset of registers. We have a subset of 12 registers, 4 argument registers, 7 call save registers, and 1 temporary register, which is compatible with what we did on the old architecture that we had. So we know that we can model almost all the software immediately on there. And that leaves us with 12 bits, leaves us with 8 or so 3-operand encodings, 16 3-operand encodings, or more 2-operand, or a set of 1 and 0-operand encodings. The blue instructions are mostly memory operations and standard arithmetic operations, so they shorten normal code accesses, stack accesses, all these things. And then the green ones are mostly encodings that address the special part of the XMOS architecture. So we can address them quickly with the pairable instruction, but they're slightly longer encodings. So this brings us close to the density we had, close enough for us to believe that we can take all our existing customer code with us into this 4th generation architecture. And then of course the final is there's the normal conventional RISC-V encodings. Right, that's the end. Any questions?
Any questions in the room? Ah, here we go. I saw somebody pointing. I thought, well, this will be a first. Somebody's going to say, hey, he's going to ask a question. But here we go.
Hi. Have you considered integrating your hardware threads with an pthread model or an OpenMP style parallelism?
That's a good question. The question is, can we, if I heard it right, sorry, there's quite a bit of echo. Can you use hard threads with pthreads? The answer is yes, you can. We haven't ported the library, but there's nothing that stops you from doing it. FreeRTOS is sort of on the way to pthreads. So it is absolutely, we support asynchronous threads, so you can use them with pthreads. There's just only 8 of them, which is slightly unusual for pthreads. Right? So people will have to be aware that when they've allocated 7 of them, that's it. You're gone.
Okay,
More
thank you.
questions?
Another question? Oh. Yes, Alan. Here we go.
Is there any way to communicate between the threads so they can coordinate besides just writing to memory and reading from memory?
Sorry.
Is there a way to coordinate between threads besides reading and writing from memory?
So the question is, can I coordinate threads so they access the same memory? Is that, yeah. So these threads all follow a hard real-time schedule. So there's nothing that stops you from actually running them completely synchronous if you know exactly what code you're executing. And you can compile time prove that they will indeed synchronize like that. So you can compile time prove that I have, say, as an example, you may want to do a convolution in a neural network that runs the same code. They will all execute synchronously, and we actually make use of that.
Well, passing results from one to the other directly instead of going through memory.
Yes.
Or something with full and empty bits if they don't know the timing.
So you can pass results. We have channels that allows you to pass results or that allows you to pass a pointer from one to the other and say, it is sitting in that part of memory, depending on how you time it, that there's asynchronous channels, there's synchronous channels. So you can synchronize, or you can choose to say, I've done my compute, here's the answer, and you get an answer back with a new buffer if you would like, for example, double buffering between two threads.
All right. Great question. Thank you, Alan. Any more? Going once? Going twice? Let's give Henk a round of applause and say thank you.
Thank you very much.